Hello everyone, welcome back to Sci Teaches. I'm Simon and I'm going to be teaching you today how to do KCL and KVL. In our next video, I'm going to be showing how to do node voltage, which is what I think to be the most enjoyable and useful topic in all of your first circuits class. It will be useful in advanced circuits and in all of your classes on MOSFETs, FPGAs, like almost everything. BJTs, Anyway, to focus on KVL and KCL and not get distracted with what the future holds, I want to start with prerequisite knowledge. Of course, as always, ignore this right side of my screen here. That is the stuff that I use to make pretty circuits that you will see later in the video. To get started, there are two main things you need to know that I haven't talked about yet in my source transformation video. The first is, what is the difference between when you have a power source that's a diamond versus a circle? Well, a diamond is a dependent current source, or a dependent power source, sorry. And a circle represents an independent power source. And what does that mean? Well, it means that this circle will be attributed some value. Let's call it V or whatever. It could be a number. It could be a sinusoid. It could be some signal. But a dependent is going to be an equation. It's going to be in terms of some other part of the circuit. Maybe a measurement, maybe some other voltage source. You don't know, some other power source. It doesn't really matter. The point is that it's dependent on something else. Pretty simple to deal with, though. The second thing is people give me feedback on the last video about power. Okay, I briefly mentioned that when doing power equations for V times I, voltage times current, it's negative sometimes and positive other times, and there are diagrams on it. And I briefly mentioned that for particularly if you have a voltage source like so, and you have a current that's going in the same direction, right, negative to positive, back of the arrow to top of the arrow, if you have that, it is negative VI. And if you have the opposite, it is positive. So we have negative to positive on our source, and here we have top of the arrow to bottom of the arrow. So they're opposite, and in that case, the equation is just regular old V times I. And the same goes for current sources. It's literally the exact same. You look here, positive, bottom of the arrow to top of the arrow, negative to positive, we have our negative. Bottom of the arrow to top of the arrow, positive to negative, meaning opposite. That gives us no negative. All right, so that's the simplest way I can explain it. You could maybe take a screenshot of that little diagram. And something that I'm going to mention later that I didn't really say was prerequisite knowledge, but is useful in all of circuits, is that things that are in parallel, this is a hideous drawing, but it gets the point across. Things that are in parallel have the exact same voltage, okay? If you have components in parallel, their voltage drop is the same. And that's to say that here, if I have some component on the left, some component in the middle, and this component on the right, and they all connect up to these same nodes, which clearly by definition means they're in parallel, and I showed this in my last video actually, that the voltage drop, I've defined it here, is the same across all components. This could be a power source. This could be a resistor. They could be like, it doesn't really matter. They could be anything. The voltage drop across all of those components must be the same value, okay? It must be the same value, and that will help you in all of circuits to come, particularly RC circuits and LC, RLC, all that good stuff, and just anything in the future. Putting things in parallel, super helpful. All right, finally, let's go and look at Kirchhoff's laws, okay? They're Kirchhoff's laws. Kirchhoff's laws always it puts a smile on my face. It's a little joke. So, what did Kirchhoff's law say? Well, let's look at current. The current law is that if you have a current flowing in one way, a current flowing in, and another current flowing in, okay? And you could add another one, it doesn't matter. If you have a bunch of currents flowing into one node, they all add up to 0, okay? And what that would mean, by the way, in this scenario, that one of these currents, I1, I2, or I3, has to be negative and is really flowing the opposite direction. Okay, so a lot of people will do a better or more intuitive, let's say, explanation that if you have a current flowing, two currents flowing in, whoops, my Apple Pencil is acting up. If you have two currents flowing in, whoops, I'm sorry, if you have two currents flowing in to a node and one current flowing out, the current flowing out is the sum of the two flowing in. And you notice this statement is equivalent to this because this I3 is defined as opposite. So it's just an easier way to understand. And a lot of people say, well, the best way to put it is, let's say you have a road and you have X cars over here and you have Y cars over here. And your output is this one road and they'll have to merge. And that output has Z cars. That means Z must be X plus Y. This is the only place for the cars to go. The same way, this is the only way for those currents to come. And then, of course, I like to add that though the 3 current setup is the most common, you can have a 4th, a 5th, a 6th, a 7th, whatever. And particularly with this 4th, let's say that this 4th is flowing out, the same way this 3rd is flowing out. That's just adding another road for the X plus Y cars to flow out of, so that would equal Z plus W. Or here, I1 plus I2 is equal to I3 plus I4. Now, KVL can be a little more complicated because it depends on your wire instantiation. Like, for instance, is this one isolated wire? Or is this, right? Is this left, or is this right and bottom one wire? Or maybe this is included and they're all one wire here and this is a standalone wire. And that's going to be the case in the example that I show you later. What that means is when you're doing KVL, you often end up dealing with currents, even though you may not, think, well, why aren't we dealing with voltages? You indirectly end up dealing with currents. And if you have a wire, right, it's along 3 sides, it all has the same current, all 3 of those wires, and that will matter. Anyway, what KVL says is that if you enter the positive terminal in a loop, if you say, I'm going to arbitrarily define a current loop, okay? I'm going to say current is flowing this direction, right? And we'll call that a current loop, I, okay? And I'm going to say I'm entering the positive terminals of my resistors because resistors are non-polar. And you should know that because when you make a circuit and you put a resistor in to wherever it's supposed to go in the circuit, if you put it backwards or forwards, it does not matter. It is non-polar. It doesn't matter. So you're technically always entering the positive terminal unless it's already been defined for you in the problem, okay? So the voltage drop here, V1, across this resistor, plus the voltage drop across this component, plus the voltage drop across this component, or this whole wire, there might be multiple components, plus the voltage drop across this one. And you notice we're always, because we're flowing in this direction, entering the positive, entering the positive, entering the positive, entering the positive, right? We're going like that, going like that, going like that, going like that, right? Those sums, the sums of all those voltages, 1, 2, 3, and 4, are equal to 0. The sum of all these voltages, 1, 2, 3, 4, 1, 2, 3, 4, is equal to 0. And it's that simple, okay? Now, you can use Ohm's law to put these in terms of current, okay? There are a few things I like to teach with this before we move on. The first of which is, if I can get rid of this, the first of which is if this source actually is positive minus, okay? Let's say this is a voltage source. Well, in my equation, this would be wrong. This would be minus plus because it's already defined for us, okay? So really, my current loop going this direction here is entering the negative terminal. It's not entering the positive terminal, which means I have to subtract. So I'd be subtracting V4. Anytime you enter the positive terminal in your arbitrary current direction, you are going to add, and anytime you enter the negative terminal, you subtract, okay? And the sum of everything is equal to 0. The second thing I like to teach is how do we get these voltages? If I have V1 and I'm instantiating a current loop, or if I don't have V1, sorry, I have like R, the value of a resistor, and I have current flowing this direction, how am I supposed to find anything out? Well, we have Ohm's law. We have V equals IR. So really what I can write is IR1, and let's say if this is all one loop, this is all one wire, and there's nothing branching off here or here or here or here, and we're saying instead there's definitely something branching off here or here or here or here, then this green line right here, all this, it has the same current, and this has its own current, and we'll call that, the current along the green I1. That's I1 times R1 plus, like, this current here, I1 times R, we'll call that R2, or R3, sorry, that's R3, plus, and let's say the current this way is like I2, well, this will be I2 times R2, right? Because these are different currents, okay? Just using Ohm's law. That's how you break these problems down. And you don't have to think about that too much. I know it can get complicated. I know I'm drawing horribly. I'm trying to teach this as quickly as possible. It's just important to note you can definitely break these down and these problems down, and you're always going to be dealing with currents. You will be dealing with currents, always. So let's go through an example. First example I have for you, we want to find the power associated with this 0.2 amp current source. How are we going to do that? Well, my thought process is as follows. I've got a defined current here, a well-defined current. I've got a dependent current source. No big deal about that. That just means it's defined as some equation, which we have there. And that's defined, just not, as well as this one. And then I can easily find a current here. Then, well, why not do that, okay? I can at least find something that might be helpful to me, okay? Another thought process you might have if you've done these kind of problems already and you think you're well-versed, right? That's for kind of if you're lost. If you know exactly what you're doing, your first thought will be, if I need to find power across a source, I need to find what two things? Voltage and current. Well, here I already have a current, and what do I need to find now? If this is crossed off the list, well, a voltage. So I instantiated a voltage over here, plus minus, and we're going to go ahead and do that, okay? So let's proceed. How do we find that? This is kind of the backwards logicking. Well, to find a voltage in one part of a parallel system, what did we learn earlier? What did I show earlier? Well, we could find the voltage drop across another part of the system, another part of the parallel system, because things in parallel have the same voltage drop. So what I instead can do, instead of finding the voltage across here, is I can find the voltage across here. And those will be the same. And I know I can definitely do that. Because I've got currents and I've got resistors. And currents and resistors means I can find voltages, okay? Now, I'm going to highlight all that, or maybe I'll leave, some of this. Let us think about how we can find the voltage drop across these resistors. Well, we need to find the current that goes across them. And that current, because they're on the same wire, this wire, that goes along here, is going to have the same current. And that's when I would think, okay, now I know what I'm doing. Now I'm going to use this current and this current to find the following current. that goes along these two resistors, and will give me that resulting voltage. Okay, so let's do that. The first way that I can think, well, put this current in relation to something is to put it in direct relation to V1 over 4, to this current source through KCL. Because I've got a current of 0.2 amps going in here, current of V1 over 4 going in here, I can definitely say that, that the 0.2 plus V1 over 4 is equal to I, this resulting current. And I put this in formal terms of KCL, where you subtract the outgoing current instead of equal to 0. But that's the same as saying 0.2 plus V1 over 4 equals I. That's the same as 0.2 plus V1 over 4 minus I equals 0, right? Of course. Now, I can also see one other relation. And that relation is, well, V1 is equal to 2 times I. And the way I see that is, well, they gave us V1 is actually a voltage drop across this 2 ohm resistor. And I know that V equals IR, and I've taken I here, so this I can substitute in there, and this R I know is 2, right? Because it's the 2 ohm resistor. So I can put another relation. So V1 equals 2I. And you know always, you should know this from algebra, if you have two ways to relate two variables, two different unique ways to relate two variables, they are solved. All you have to do is do a system of equations. Here I did a linear system. I simplified them in different ways to cancel out the V's, and then I found a resulting current. And from that current, I found the voltage. And of course now, that will allow you to, with the current and the voltage, find the total voltage drop across this wire. The way we do that is, well, first, ignore me erasing this, so it's just 2.4 volts. Sorry. The simplest way to put this is, well, what's the voltage drop across this resistor? It's V equals 4 times I, and I is 0.4 amps. So 4 times 0.4, I wrote that down here, and that's going to give us 1.6 volts. That's the voltage drop across here. And the total voltage drop is that voltage drop, the one from here to here, plus the voltage drop from here to here. Okay? It's those two voltage drops combined. So that's 4 times 4 times 0.4, which is 1.6, plus V1, because we don't have to calculate anything if we already have V1, right? And V1 is 0.8 volts. So this is 0.8, this is 1.6. So the total voltage drop, V, is equal to 2.4. That's equal to V. And then now, of course, I have a current. I have an associated voltage I found here and here. So I can definitely now find power with VI, one of my VI equations. All we have to determine at this point is, well, is the VI equation using negative VI or is it using positive VI? And how do we figure out which? And the way we do that is, give me 1 second. The way we do that is we look at orientation. We see an arrow that flows from this current source right here, bottom to top, and the voltage we've just found is negative to positive. So they're the same orientation, and that means that the sign needs to be flipped. So we're going to add a negative. Negative VI is our resulting equation. Negative 2.4 times 0.2 from that original source is equal to negative 0.48 watts, and that's going to be our final answer. Example 2, I'm going to try and kind of walk you guys through my first thoughts before even attempting to solve the problem, because this one I think it's a little bit more clear once you've had the experience of that first problem to come up with your own thought process. So my immediate thoughts are, with KVL and KCL, I can first create a direct relation to two currents, okay? And I think that's the best I can do. Obviously, if I could find Vx directly, and I'm sorry, I never specified, this problem asks you to find Vx, which is across this 3 ohm resistor, and it asks you to find the power associated with this 10 amp source over here, okay? If I could find Vx directly, that'd be fantastic, but it doesn't look like I can. So the best I could do is maybe directly relate to unknowns, two variables. And so I've instantiated some current going this way and current going this way because I can. You can say current's going whatever way you want. And that the reason I've done that is because I need this I2 to find the Vx across this 3 ohm resistor. Because if I have R and I can find I can find V. Okay? So I can directly relate these two currents, I2 and I1, and I know that if I can directly relate those two currents in another unique way, that the problem is solvable. So maybe I can try, if I've just used KCL, I could try KVL. And with KVL, I see, oh, I've got a loop here. I can define current in whatever way I want. And I've got I1 flowing through this 4 ohm resistor, flowing up here, I1 flowing through this 3 ohm resistor, and I2 flowing through this 3 ohm resistor. Isn't that another direct relation that's unique? It certainly is. So I'm going to create those two direct relations between I1 and I2, and then that third step is to solve the resulting linear system, or use substitution. It doesn't really matter what algebraic technique you use. So let's do that step 1. Step 1 here, we have I2 is equal to I1, which is going here, plus 10. This is 10 amps going this direction, okay? That's our KCL. And you'll notice I write it differently here, and that's just personal preference, and I'll explain why I did that in a minute, but let's move on to step 2. So step 2, we then do our KVL. I instantiated a loop going this way. I started right here. Well, we're going through the negative terminal of this 10 volt source, so minus 10. Then this resistor has not been defined, so I can just say plus minus, because resistors are nonpolar. It doesn't matter what direction you flow through, unless some positive negative has already been defined, like it is for Vx here. It does not matter. It does not matter at all. So I'm going to add 3, because I'm positive minus. Then I'm going through the positive of Vx. So plus I2 times 3, which is equal to Vx, by the way. And then I can make a plus minus on my own again. And that's again using I1, because this is all the same wire here on this right side. These 3 sides are all the same wire, all have the same current, I1. So I'm going to add that again. So you notice going through the negative terminal, you subtract. Going through positive terminal first, you add. Okay? Then I've got 2 equations. I can directly input whatever I want. This was my own personal preference here. But I did it because if I put things in terms of I1, right, or I1 in terms of I2, then when I substitute, I can plug in for all my I1s a resulting I2 equation, and then I can directly find I2. And that way I never have to find I1 because I don't need it, and that would just be me wasting my time. And it's very important for you guys to look for those patterns. How can I substitute more efficiently? How can I find I2 without having to find I1 itself, to make it so I can be faster in tests, in quizzes, when there's a time crunch? So I do just that. We find I2 to be 8 amps, and then we use that little parallel trick yet again. We know that Vx here, plus minus, across this 3 ohm resistor is the same as the voltage across this 10 amp source, right? Because they're directly in parallel. Okay, so we're going to plug in. We have that voltage. We have that voltage of Vx, which will be 8 amps from I2 times the 3 ohms, so 24. And that was the answer, by the way, to part A, was to find Vx. So we've done just that. And then using that 24 volts as V for our VI equation to find power, we just need to look at orientation. Well, Vx is positive, negative, and the arrow is going from the negative to the positive. So it's the same orientation. So we need to add a negative in there. And let's do that. So we have negative VI. Okay? And now we just have to solve the equation. Negative VI is negative 24 volts times, what was our amperage? 10 amps. And that gets us negative 240 watts. And that's going to be our answer. I'll see you guys next time in my video covering node voltage. Thank you guys very much for watching. And let me know if you have any feedback or if anything's confusing. I'd be happy to teach.